Yeah, look, good morning, everybody. I just want to present the work that we've been undertaking on the APSIM Next Generation Canola Model. People such as Jeremy Wish and Julianne Lilly have been heavily involved in this effort as well. Neville Herman has helped with assembling some of the data sets, and of course, Dean Holsworth as well. Yeah, the canola model has been developed using the plant modelling framework in APSIM NextGen, and most of the components and designs are similar to the other models that we've developed inside the plant modelling framework. And so I won't go into a lot of detail, but for example, the structure here is very similar to models such as the soybean model that you'd be familiar with. It includes the plant arbitrator that looks at the arbitration of dry matter in various forms and nitrogen within the plant. There's a phenology model, which I'll describe in a little bit more detail. And then we have the standard models for the roots, leaf, grain, stem, and shell. There's also a composite plant organ called pod, which aggregates the grain and the shell components, so that you can compare that against observations of pods, which is also important for canola. And there are various other composite organs that allow you to provide outputs for above ground biomass or live biomass or below ground biomass, okay? In terms of phenological development, there are a range of growth phases, and they're somewhat similar to the traditional canola model in APSIM Classic, but also bringing in some of the ideas from other models in NextGen, such as the soybean model. So the phenology model goes through various growth phases. There's a germination phase. The plant then goes through an emerging phase. Once that has started or completed, there's a vegetative phase. During that vegetative phase, which extends up to floral initiation, there's a vernalization processes going on. So the duration of that vegetative phase is driven strongly by temperatures. After that, there's a bud development phase. The duration of that phase is driven by the appearance of leaf primordia. So we're predicting during the vegetative phase, we're predicting the final leaf number. And then with the bud development phase, we grow out those particular leaves from the plant. We then have a stem elongation phase. That phase can have a photoperiod effect, though as with many brassicas, it's not often a strong photoperiod effect. Most of the phenology or variation in phenological development is driven by vernalization in the model. We then go through a series of phases. There's an early flowering phase, and then an early pod development phase, and then three parts of grain filling. For example, in the early grain filling phase, goes from the start of grain fill through to the end of flowering. The mid grain filling goes from the end of flowering to end pod development, and then the late grain filling goes from the end of pod through to the end of grain filling. And then we just have a simple maturing and ripening phases. The model has been tested across 10 locations across Australia. Within the validation set that we're presenting today, there are 1,164 simulated crops across those locations. And those locations have been chosen from a larger data set that we've got based on the quality of the data and what it can provide to us in terms of model development. Within the validation set, just to help us to understand and navigate that number of simulations, we've broken things down into experiments that are purely for phenological development. In those experiments, there's measurements of leaf appearance rates, timing of floral initiation, flowering, green bud and stuff like that. In the growth, there's also growth experiments. Those look at the growth and development of the plant. They may also include phenological observations. and leaf appearance sort of data, but they look at growth responses to a variety of agronomic interventions, sowing dates, varieties, nitrogen rates, and the like. In terms of the testing for phenological development, across those data sets, it includes quite a broad range of growing conditions. So I've already mentioned that temperatures are the major driver here. And if we look, there's quite a range of growing conditions. What we have there is a graph of the mean temperature against the days after sowing for all of those experiments. We can see there's a range of about 20 degrees in mean temperature for various timing of after sowing. So that gives us a good data set. And there's also photoperiod extension data sets inside that as well. So it's quite a thorough testing of this initial version of the model. The test for the growth experiments, the temperature range is not quite as wide, but it's still about 10 degrees across all of the various growth stages. It's not as wide because they're usually targeting normal growing conditions, albeit across a range of growing environments across Australia. So once again, it's quite a good test data set. Within those tests, this is just one graph of an example test data set that we have. And this is for a place in Southern Australia, Wagga. And in this case here, you have a variety of growing conditions or dates. And we can see there, and inside those data sets, we have good measurements of canopy development in terms of leaf area, biomass accumulation, and partitioning between leaf and stem. And that's a good example of the types of data sets that we have chosen as part of the validation sets. That's just a screenshot from some of the combined results across what we've done. And there's a range of growing conditions, and there are sites where the model's working or it's not. All of this is in GitHub. People should have seen that already. It's been, the work has been undertaken within the under review folder there for the last few months. So it's been available up on GitHub, and they're the range of sort of statistics that we have up there. And you can get some idea of the number of measurements in each of those, for each of those sort of measurements there. We also have, as part of that test, a series of sensibility simulations. So we haven't just tested against data sets itself. We've extended the testing with sensibility runs, and people should be familiar with what those are. The first one, for example, there is looking at demonstrating the detailed within plant dynamics. And within those sensibility tests, there's a demonstration of how the arbitrator is working. And then for each of the main sort of above ground organs, for leaf, shell and stem, graphs that demonstrate the growth and senescence of the various organs and the retranslocation of N in and out of those organs, and then reallocation to either senesced mass or retranslocation. Because canola is also a dual purpose crop, and that's a growing application of that, we also have, there's another, I should talk to this sensibility test here. There's also a test, because the one difference to the other crop models here in terms of the released models is that the model also allows for photosynthesis and resource use through the pods. People should be aware that with canola, early growth and photosynthesis is undertaken via the leaf canopy, and later in the season, it's most of that is being provided through the pods. So in the graphs here, we can see there's a plot of canopy area over time, and then later in the season, an estimate of the area of the pods. That then transfers through into predictions you can see of light interception And so we can see again early in the season, it's basically all of the light interception is undertaken or provided by the canopy. But as the pods develop, light interception then becomes dominated by the pods as the leaves senesce. And that follows through into the timing of transpiration and the water use from those various organs, you can see in the bottom left. But also the fixation supply, which is the carbon fixation or photosynthesis, the timing of photosynthesis via either leaves or late in the season, the pods. The other sensibility test is, as I was saying, was for canola as a dual purpose crop. And so within the crop here, we've got a simulation, once again, for Southern Australia, where we have plugged into the same simulation some livestock. So we have livestock being put in. We have a winter canola planted in March, with livestock being put into the simulation in sort of late May and grazing it for about 10 days. We can see as a result, there's the biomass of the plant being impacted under the two stocked simulations. We've either got 0 livestock, 10 or 20. These are cattle, I think, in this simulation here. And that is impacting on the canopy or the leaf area of the plant and the leaf mass. What you can see in those simulations is that even though there is the crop is grazed early, and this is mostly prior to stem elongation, and there's not much stem mass at that time, the plant is able to compensate with that sort of defoliation. So thank you. That's a brief description of the model.